Open the lid, pour in the hot water, and enjoy. All that's left afterwards is the packaging. What do we do with all the plastic waste? Or could we manage without plastic? Welcome to Tomorrow Today, the science show on DW.
Pot noodles have been a favourite for decades. The Japanese version is especially popular among young people. It's known as ramen, a super fast food appreciated by busy students. The broth paste and herbs are packaged in plastic. For an EU competition, a group of graduate students took on a challenge. Could the seasoning be packaged in something non-plastic and edible? Maybe eggshells? They're not actually part of the egg that we consume, but they're still an important resource for us. They also contain interesting properties that could help us create better food packaging. Whether hard-boiled, soft, or raw, eggs are delivered in their own ideal packaging, and they're plentiful. Every year, Germans alone eat 20 billion of them. So Team Edgy decided to focus its research on eggshells. They're from the University of Hohenheim near Stuttgart. It's one of the best in Germany for food science, with a lab that makes all kinds of experiments possible. The team spent 9 months conducting intensive research into edible packaging. In that time, they perfected the formula. It's made of finely ground eggshells, heated and sanitized to be hygienic, a vegetable protein and a binding agent. The exact composition remains a secret. Add water, mix well, then pour into a tray. Drying it out in the oven creates a thin film that behaves like a plastic bag. Another practical property of the film is that it reacts to heat and can be fused together after the contents have been added. This means it can be sealed into separate portions. It's a very simple product, a cup of pasta and a seasoning sachet. Add hot water and the sachet dissolves in a split second. Stir it all together and that's it, an environmentally friendly snack without plastic waste, winning Edgy the first prize in the competition.
Could the packaging succeed in retail food markets? I would say the chances are 50-50. Right now, the situation is quite favorable because companies are looking for new solutions, and this is an interesting solution.
The students are already hoping to get a commercial partner with a view to founding their own startup. It was great to eat my first pot noodle with our packaging. And evidently, sustainable noodle soup creates sustained satisfaction.
We use it for food, water bottles, detergents. Plastic is everywhere. But what is plastic exactly? What is it made of? And why does it stay in the environment for so long?
It's a material that's been part of our lives since we were born. Cheap, sterile, and practical. Plastic has assumed various roles over the decades as toys, accessories, utility products, and a dream for innovative designers. Plastics consist of large molecules called polymers, which are generally manufactured from mineral oil. The oil is broken down into its constituent components, which are then recombined to create synthetic polymer chains. The new material has very special qualities. It's light, robust, and can be molded into practically any shape you want. But plastic's not as easy to dispose of. The synthetic polymers are almost impossible to break down and degrade extremely slowly. Some need 500 to 1,000 years to fully decompose. Plastics are great for mass production, but not all of them are made from oil. Some polymers are naturally occurring. and are used to make bioplastic. Corn, sugarcane, and cellulose can be chemically converted into molecular chains with comparable properties to oil-derived plastics. They degrade easier, and even if it takes them time to do so, there's obviously a need for non-fossil-based solutions. 90% of plastics are manufactured from oil. The amount recycled or qualifying as bioplastic is not even 10%.
So where does the plastic that doesn't get recycled end up? A lot of it enters our rivers, and from there it's carried out to sea. Our oceans are drowning in plastic. A team of scientists is analyzing what happens to the plastic left in the water.
These plastic tags have been floating around in this water for almost 2 years now, and they'll be there for at least another 8. One of the tanks is filled with fresh water, the other with seawater.
You can see it's coated with quite a layer of salt. The seawater is certainly having an effect.
It's part of a long-term study being conducted at a university in eastern Germany.
Basically, in this experiment, we're looking to see how plastics decompose in water. In particular, we want to know whether they can be recycled after being in water for years.
The researchers from Magdeburg's University of Applied Sciences are especially interested in what long-term water exposure does to normal everyday plastic waste. How does it change its structure? How are the surfaces affected? Generally, we're concerned with what the material does to the ecosystem, the water. But we're looking at what the water does to our plastic. Can we really get it out of the water and use it again? The plastic is being exposed to natural influences in as many different environments as possible. These tags have been floating in the Baltic for 18 months. Those are barnacles. But we also have bivalves.
And that's seaweed. You can't recreate that in a tank.
The team of scientists are hoping for a lot of new insights. Ones that will help us to better fight the growing tidal wave of plastic in our oceans. New studies are warning of an exponential rise in the amount of trash in our seas. By 2050, there could be more plastic than fish in the sea.
Every year, a total of about 300 million metric tons of plastic is produced. At least 10 million tons end up in our oceans. That's the United Nations estimate. You could say a truckload of plastic is dumped into the sea every single minute.
Plastic can take hundreds of years to break down. It's practically invincible. In water, it decomposes slowly into microplastic, and then, often as not, it sinks down into the depths of the sea.
It's estimated that already 80% of plastic is already lying on the seabed and can no longer be removed. There it gets eaten by worms and all kinds of organisms. In short, it lands back on our plates via the food chain, via the fish we eat.
Many green organisations are trying to break this vicious circle. The Ocean Cleanup is probably the best known project. It uses floating structures to capture marine litter. One Earth, One Ocean is pursuing a similar goal, using boats to gather up the plastic, sort it and recycle it. Then there's the Everwave project, which involves trying to remove litter from rivers before it can even get to the sea.
On the one hand, these projects raise awareness of the issue, warning us about our use of plastic. On the other, they are a drop in the ocean. What we are currently dumping into the seas can't be removed by any project or with any technology in the world.
Michael Steiger agrees, but he's determined to do something to curb the plastic. As well as the big projects, there are small businesses like his attempting to recycle marine litter. He and his team produce rucksacks made completely of plastic from the ocean.
There are already a lot of great projects out there. The more, the better. And we think that all these projects combined are also having an effect on the environment.
In the Philippines, some 100 people gather plastic from the waters off one of the archipelago's islands. The Pacific Ocean throws up a lot of trash on the beaches here. Most of the plastic has only been in the water for a few weeks or months.
We can recycle about 20%. The other 80% is made up of plastic-coated wrapping paper. You can't recycle that anywhere in the world, including Germany. They are incinerated. This is the only currently existing way of getting rid of these materials.
Only marine litter found close to the beach is used to make his rucksacks, as it's unclear how suitable plastic is that's been out at sea for years. In the future, science could shed new light on that. Back in Magdeburg, the experiments currently being carried out don't offer much hope. The material is so contaminated, cleaning and preparing it to get to a point that it could be turned into something new is so much effort. The chances of cycling this trash are slim. And amid all this research on marine litter, they say it's important to bear one thing in mind. The message can't be, no problem, we can recycle it. We can't let that stand. It shouldn't end up there in the first place. And we will need to keep on researching over the next few years to find out what we can do with the plastic if it does end up there.
The ideal solution for the world's waste problem would be a plastic-eating Pac-Man. He'd need a huge appetite, be able to eat fast and digest plastics like PET that's used for water bottles. Amazingly, scientists have discovered an enzyme that can do just that.
Researchers in the city of Leipzig have found an enzyme that breaks down plastic very fast. But to work, it has to be heated to between 60 and 70 degrees Celsius. Christian Sonnendecker's team believes biotechnology holds the key to our plastic problem. We look at how nature does things and then copy it. And nature uses enzymes to break down polymers, so that's what we're doing. The team heads out to one of Leipzig's main cemeteries. This is where they found their enzyme, on a compost heap. Let's see what we find. The researchers identified an enzyme that decomposes leaves, and it can also break down PET plastic. Leaves have a wax-like coating formed by an outer layer of cutin, which is a polyester. That's a polymer that's built up via ester bonds, just like with PET. It's the same from many bioplastics too, and the enzymes are so non-specific that they can recognize and break down a broader spectrum of polyesters. That's the advantage. We're lucky to have a biological answer to our plastic problem. Christian Sonnendecker showed us how fast the enzyme works. As long as it's kept at 60 to 70 degrees Celsius, the PET packaging dissolves completely in one day. All that remains is the basic building blocks. The enzyme was a lucky find for the researchers. We've called it PHL7, which stands for Polyester Hydrolase Leipzig, and the 7th candidate out of the 9 that we found. That was the best performing enzyme. And this is what it looks like. They produced a 3D printed model to show how the reaction works. Here's the enzyme and here's the PET chain with the ester bonds, the links that will be broken. The enzyme comes like a Pac-Man and nibbles off the individual ester bonds, leaving the basic building blocks terephthalic acid and ethylene glycol. And from them, we can make new plastics. Christian Sonnendecker's team have now moved on to the next step. They want to modify the enzyme's DNA so that it eats plastic even faster. To do this, they're experimenting with many different modifications. They analyze each variant individually, selecting the most efficient ones for further study. They're also turning to modern technology and artificial intelligence to help. Biotechnologist Ronnie Frank is assisting them. We now want to scale up our technology, so we have our new prototype here that will allow us to analyze around 100 enzyme samples at once, studying multiple layers at the same time. That will generate the data we need to feed our AI, to then train it to identify new improved enzymes that can break down plastic. They're analyzing thousands of enzymes each day in search of a super enzyme. And they have a larger vision too. Ultimately, we want to get the market to work more with polyesters that are easy to break down with enzymes. That will allow us to develop really efficient circular economies. We have no alternative because right now we can't cope with the plastic waste. So we're looking to the future, and we're having a vision of recycling plastic waste sustainably.
Most plastic is made from crude oil, which was produced long before we came along. Arnulfo Quintanilla from El Salvador sent us a question about that.
How is crude oil made? Crude oil wouldn't be possible without these small marine animals and plants, plankton. It's not just food for sea creatures. The petroleum being extracted today formed over millions of years from tiny creatures just like these. As soon as plankton dies, it sinks to the bottom of the sea. Since there is barely any oxygen at greater depths, the plankton does not decay. Instead, it mixes with different sediments, like clay and sand, on the seabed. These sediments flowed from rivers into the oceans. Together with the organic plankton, they form decaying sludge, the source for rock petroleum. Over the course of 10,000 to several million years, sedimentary layers stack on top of each other, becoming hundreds of meters high. This process increases the pressure on the petroleum source rock and raises the temperature. When the temperature reaches 80 degrees Celsius, the petroleum source rock begins to transform. The long-chain hydrocarbons that make it up break into shorter chains. This process is known as cracking. The fine-grained, digested sludge transforms into viscous crude oil, one of the most complex organic compounds on our planet. Extreme pressure forces the oil out of the rock. It migrates upwards and collects beneath impermeable layers of salt or solidified clay, creating an oil deposit. Today, about 15 billion litres of the black gold are extracted from deposits every day. New crude oil is still forming all the time. As long as there is plankton, there are the substances needed to form petroleum. But it won't be ready for millions of years.
Petroleum has been powering industry for the past 150 years and driving climate change too. Electricity is one alternative, but electric cars, for example, need rechargeable batteries, and they're stuffed full of precious raw materials, so scientists are looking into how to recycle them efficiently.
A black box, and inside, chunks of old batteries. They might not look like it, but they're very valuable. Inside are lots of rare metals, including the much sought-after lithium. The company Acorec in Krefeld, Germany, has been recycling old batteries from across Europe for more than 20 years. Engineer Rainer Seuker is a battery recycling pioneer. He thinks battery recycling has untapped potential. The market is huge right now, but relatively few batteries are being returned because many countries still don't have the collection infrastructure. The awareness of how batteries are collected for recycling is not very pronounced here in Germany either. Other countries have higher collection rates. Lots of batteries get mixed in with electronic waste or they're exported in such a way that we're not able to trace their routes. So the overall return rates are pretty bad. In fact, less than half of all batteries get recycled. That causes big problems for recyclers. There's not enough demand to build the recycling machines needed to carry out the process. In this pilot plant, depleted lithium batteries are being heated to 550 degrees Celsius. We developed this treasure here ourselves. It's a pilot plant, a larger one that will go into operation in a few weeks. Plants like this one don't exist anywhere on Earth. These batteries have only been on the market for 5 to 10 years. Demand for them went up quickly, and now they're being recycled. Recycling itself is still very young, and that's why pilot plants like this one are enormously important if you want to recycle on a large scale. Soon, large amounts of lithium-ion batteries will be ready for recycling. These gold-colored crumbs are clay minerals used to safely store lithium-ion batteries, which are prone to catching on fire. Sorting batteries is still laborious manual work. Their components are very different, but from the outside they're virtually indiscernible. There's no description of which chemicals are inside, so each battery is a unique surprise. Right next door, recyclers are working on a destroyed car battery. It might still have some residual charge in it. That's why special high-voltage electricians are at work here. Engineer Rainer Seuker says it's worth the effort due to the value of the coveted contents. If we just focus on the metal lithium, it's one of the metals that's most available on the planet, but it's very finely distributed across the Earth's crust. Here we get the material for free inside the lithium batteries in a concentration of 2, 3, 4, or 5%. So these are, of course, an easily accessible source. Why extract it very laboriously from nature when I can get it free of charge when recycling? Lithium recycling may soon become big business, but at the moment it's still in the pioneering phase. The batteries have just come out of pyrolysis, where we've removed the plastics and adhesives. And now we're left with a material mix of metals like steel, aluminum, copper, and black mass. We now have to separate those metals. We're working closely together with RWTH Aachen on this. RWTH Aachen is one of the leading institutes in Germany when it comes to recycling used batteries. Scientists like Paul Zabanai develop recycling concepts for all types of used batteries, including this used ion battery. The coveted raw material is in the black dust between the thin copper foils. The first step is grinding it all into a fine powder. The black part, the active mass, also known as black mass, contains all the valuable materials that make up a battery, from lithium to nickel to cobalt to graphite, all of which are extremely rare but critical according to European standards. That's why it's very, very important that we can extract the individual elements out of the black mass. Currently, 16 PhD theses are being written simultaneously on lithium recycling. Lilian Schwich has specialized in what is known as hydrometallurgy. In this process, the black mass is stirred into water. The lithium dissolves into the water, but the other metals do not, which makes them easy to filter out. Lilian Schwich transforms the black broth into a clear solution. Around 90% of the lithium contained in the black mass gets recovered this way. It's laboratory work on the verge of becoming an industrial process.
The lithium in the water here is ionic, and we can recover it from the solution using environmentally friendly processes like membrane technology or ion exchangers. When we do that, the lithium we get looks like this. You see a white powder, which is lithium carbonate, a product that can be sold in this form. It can then be reused in the production of new batteries.
Scientists and industry are predicting that that will be the case in the coming years. Extracting elements like graphite, copper, iron, nickel, and cobalt from old batteries is way past the laboratory phase. Now the focus is on extracting lithium industrially, the white gold of the green energy transition.
If our blood is red, why are our veins
Warum lieben wir die Stille?
Do you have a science question? Send it to us as a video, text, or voice message. If we answer it on the show, we'll send you a little surprise as a thank you. So come on, just ask. That's all for this week's edition of Tomorrow Today. Join us again next week for more science stories. Until then, stay curious. Bye-bye.